morning. Hello. Thursday, May 7th. Welcome to another edition of Kitchen Table Chemistry, and thank you for joining me. Today's topic will be acid-base equilibria. Now, the equilibrium of an acid or a base solution, we're going to treat this a lot like we did the other equilibria solutions, but they are specific to an acid or a base, and we'll spend most of our time on acids. So we'll be looking at Ka. That is the acid dissociation constant. No longer just labeling it K, but now Ka if it's an acid, or Kb if it is a base. That will be the base dissociation constant. So it's going to be one or the other. The other K value that we will use a little bit here is Kw. Kw is the self-ionization constant of water, which we looked at a bit in that pH review, and that will pop its head up from here and there, not too much. Now, Ka of a weak acid looks like this. Ha, which is your non-dissociated acid here, is going to dissociate into a hydrogen ion and its anion. So this hydrogen ion and anion will always be the products, and Ka will set up like this: the hydrogen ion concentration times the anion concentration over the non-dissociated acid concentration. And we're only going to look at monoprotic things here, so these will never have coefficients, and it will never have powers to them. The really cool thing about this is that this is going to end up being our pH, or it will come to us as pH. So oftentimes we're going to know that, and that's what makes these guys different. With Kb, it's the same idea. We'll have our non-dissociated base on one side and our cation and our hydroxide on the other side. And then again, we're going to know this. And this a lot of times will give us POH, or may arrive to us as POH. And therefore, we'll be able to determine the pH from that as well. So that's how these guys work. What else? A couple ideas here. Kw is equal to Ka times Kb. So if you know what Ka is, you know what Kb is because they're related through Kw. And then Kw again is 1.0 times 10 to the minus 14. Also, there's something called pKa, which is roughly the power of Ka, and it's just like pH in that it is the negative log of the Ka value. And so it's easy to find. It's the same way. And then pKa plus pKb will add up to 14. So if you know what pKa is, you always know what pKb is. If you know what pKb is, you can go back and find what Kb is, type of thing, and we'll have to run around with this. Okay. Here is a very typical example of what we would want to be able to do here to start with. We've got lactic acid, which is what's in milk and makes it sour, and it's what builds up in your muscles when you've exercised a lot. It has a concentration of 0.100 molarity and a pH of 2.44. Calculate Ka, calculate pKa. The first thing we want to look at is our dissociation reaction here, which will be HC3H5O3, and it is going to dissociate into a hydrogen ion and a lactate ion. So that's our reaction. Our Ka expression, Ka, is going to be equal to the hydrogen ion concentration times the lactate ion concentration over the non-dissociated acid concentration. So that will be our expression. Now, I'm going to make an ice chart, and I really suggest you make ice charts with these things. So I'm going to come over here on this side, and I'm going to go initial, change, and equilibrium. And the initial for the non-dissociated acid, and then for the hydrogen, and then for the lactate. Okay, initial here, it says it was 0.100, so that'll be a minus x. So at equilibrium, we're going to have 0.100 minus x. Initials here were 0 and 0 before there was any reaction taking place. So they're going to be plus x and plus x. So these will be x's like that. And that's how my ice chart will look. Okay. Now, It says here that the pH is 2.44, so that's going to let us know what X is. So because this is the hydrogen ion concentration is equal to that, let me just change a color here. That means that this is going to tell us what X is. So if I take the inverse log of negative 2.44, that will equal my hydrogen ion concentration. And I did that, and I got a value of 0.00363. Okay, so now I've got that value. I can feed that into my Ka expression here. So Ka is going to be equal to 0.00363. Check that. Yep, that's right. Times 0.00363. Because hydrogen will always be the same as the anion, so that works out like that. Now on the bottom here, 0.100 minus 0.00363. So it works out like this. And then we just math our way out of that. I strongly suggest that you do this step here ahead of time, or that you at least bracket it. I get a Ka value then equal to 1.37 times 10 to the negative 4. Remember, there are no units on that Ka value. It just sits like this. The final piece of the puzzle here was pKa, and that would equal the negative log of Ka. And so that would equal the negative log of 1.37 times 10 to the negative 4. And therefore, that would equal, I got for that 3.86. And that would be our pKa value. All right, so here's an example. We started with an initial concentration, quite typical, and a pH value. And from that, we were able to figure out what Ka was and pKa from that. This is, I'm going to ask you to practice a little bit of this as we go, and then we'll start putting a little bit of spin on it, doing some KB type stuff as well. We'll spend a couple days on this, and then we'll be probably to the end of this unit on equilibrium. So hope you're doing well, and that on this hopefully nice Thursday. I'm taping this on Wednesday, and it is crappy out there. So boo, and that. Take care as always. Hope you're safe. Bye-bye.